You're listening to Let's Talk Creation with Todd Wood and Paul Garner, the creation show where we learn, grow, and worship.
Well, hey, we're back for another episode of Let's Talk Creation with Paul Garner and Todd Wood. I'm Paul Garner.
And I'm Todd Wood.
Don't forget to like and share our episodes and click that subscribe button, hit the notification bell. That would be a great favor to us. It really helps to grow our audience and tell your friends, of course. Keep telling your friends about the podcast. There are lots of people out there who haven't discovered us yet and would really appreciate, I'm sure, the episode. So spread the word, Today, we are going to be continuing one of our intermittent series. We've got several of them going.
Yes, and this has been a while.
It's been a while. So, it's been, I think, over a year since we picked this one. This is our radiometric dating series.
And people keep asking if we're gonna ever come back to this. Are you gonna ever finish that series? Yeah. Eventually. Well, here it is.
It's been on the agenda. So here it is. So I thought, because it's been such a long time since we last did one of these episodes, we ought to just briefly recap.
Mm-hmm.
So we began the series way back in episode 26.
Wow.
Where we introduced radiometric dating. The podcast was young in those days. So we introduced radiometric dating. We talked about the basic principles and assumptions that were involved. And then in episode 35, we had a special guest. We had Dr. Ben Clausen, who is a nuclear physicist who came on to talk to us, dig a bit deeper into radiometric dating and tell us some things from his experience of actually radiometrically dating rocks. He's done work on granites. So that was episode 35. And then in episode 40, we talked about the RATE project. RATE stands for Radioisotopes and the Age of the Earth. And we sort of introduced this project. It was a creationist research program that investigated the topic of radiometric dating from a number of different perspectives. And many people will know that the RATE project proposed this idea of accelerated nuclear decay, that there were episodes in the Earth's past, perhaps during Creation Week and during the flood, when there were episodes of fast nuclear decay. And then in episode 44, we kind of looked at some of the criticisms that had been made of the RATE project. And in particular, we looked at an article that was published by Randy Isaac of the American Scientific Affiliation. And we kind of went through his article and we sort of responded a bit to some of the criticisms that he made of RATE. So that's what we've done so far in this series. And until now, that's kind of where the series has rested. But we're going to pick it up today and revisit the RATE project. And I'm very pleased to say that today we've got a really special guest, because we've got one of the actual RATE scientists here with us, Dr. Russ Humphreys. So Russ, it is really great to have you here. We're really pleased that you were able to come on the podcast.
Well, I'm really pleased to broadcast about this. I feel that people don't understand it very well. So let's do it.
Yeah, that's great. Yeah. Well, hopefully we can shed some more light on these things. So very, very welcome to the program. Anyone, I think, who is remotely familiar with the world of creation research will know something about you and your research interests, because you've made a number of quite important contributions over the years. And I thought perhaps for those who are a bit less initiated, it might be good just if you tell us a bit about your research career and maybe some of the areas of creation research that you've published in and some of the things that you've done.
Okay, well, a lot of my research is in the secular world. I worked for General Electric Company for 7 years, and then for Sandia National Laboratories for 22 years before I retired from them. And so a lot of my research was actually very useful for God to train me in. I got hands-on experience in all sorts of fields of science. But my creation research centered on the age of the Earth and the age of the universe, all sorts of things related to that. So early on, I did a paper with Steve Austin on the amount of sodium in the ocean. And we pointed out that there was too much going in and not enough leaving for it to be in equilibrium. And so that sets limits on how old the ocean could be. And those limits were much too young to suit the uniformitarians. Then, let's see, I did a lot of work over many decades on planetary magnetic fields, the Earth's magnetic field. And I did work on that. I made a theory about how God could have started up the magnetic fields of all the planets and the sun and the moon. And then I could work out from that theory what those magnetic fields should be today, how strong they should be. And they fit all the planets that had been visited so far, including the Earth. But there were some planets that had not been visited, Uranus and Neptune, were still to be visited by a space probe. So I said, I'll go out on a limb. Here's what my crazy theories should say about their strength. And the evolutionists, the uniformitarians, had made a different prediction for the planet Uranus. And the two predictions were a factor of 100,000 apart. So Voyager 2 went by Uranus and measured just about exactly the field that I had predicted, or my theory had predicted. And then it went on to Neptune and measured the field that I had predicted. The other side, when Neptune got passed, they said, well, okay, we were wrong about Uranus, but since Uranus and Neptune are sort of sister planets, and we predict that Neptune will also have a strong field like Uranus did. So their side got one right, by predicting rather late, and I got two. And there's some other planets that I had printed predictions in the Creation Research Society Quarterly about planet Mercury and Mars, and I had made predictions about all the planets in the solar system. And a space probe visited Mercury again. It had been visited a long time before, but it visited Mercury again and verified the predictions I made for that planet. That was, I think the last one came true in 2012. So I had a lot of fun, and it's fun to see a theory actually work out and be matched by what's in the real world. Let's see. What else did I work on? I worked on some other things. Of course, I worked on how did light get here from distant galaxies, and fit in with the idea of a young universe and a young world. And I did a book on that called Starlight and Time. And since Starlight and Time, I've had a second cosmology that was just published in Journal of Creation some years ago. And then I've now got a third one. And each one is quite different from the predecessors, but there are some common elements to them. So I've published a third one in Journal of Creation last year. So, and all of that is designed to fit in with the time problems we see. Why does the universe look so old if it's so young? And how did light get here from the distant galaxies? So I've tackled those problems. A number of other creationists have generated cosmologies, and I think that's just great, because the more there are, the more likely one of them is to be right. So I'm just pleased to see other creationists getting involved in that field. Let's see what else. Oh, and then of course there's the rate work.
Yeah, and that of course is what we'd like to talk about today. But I mean, you've made so many contributions over the years. I can remember reading those articles about planetary magnetism back in the mid to late 80s in the CRSQ, and it was very gratifying to see those predictions work out. And of course, we've kind of followed the starlight and time research as well.
Yeah.
So that's
can I jump in here? Of
course.
Back in I think it was 93, maybe. I actually went to my very first creation conference in Grand Rapids. It was a CRS meeting, and you were there presenting for the first time. I heard your starlight and time work on the white hole cosmology, and I remember.
Was that an ICC, an international conference?
No. This was a CRS board meeting, and they were having a little public thing on the side, and invited people who were in driving distance to come and hear it. And it made a big impression on me, because it was sort of one of the first times where I really felt like I heard something that was really sort of trying to tackle head on what the true history of the solar system and the universe might be. That was a big deal. I was a junior in college at that point. I was quite young, and so I've
you were
appreciated.
Young and impressionable then.
Yes.
Okay. And now you've learned better. So.
Yeah. So I've appreciated your work for years. So I wanted to thank you for that.
Yeah, that's great. Well, we would like to talk to you about the RATE project, of course. And as we said in the introduction, our viewers, at least if they've been following this series so far, already know a little bit about the RATE project. But we would love to hear your own account of the RATE project, and particularly how you got involved in it. So just tell us something about RATE and what it was all about.
Okay. RATE was if I'm going to show a picture of the RATE people
Sure.
if I can share my screen right now. There we go.
There we go.
You should see a picture of the 7 RATE scientists and 1 Hebrew expert and 3 other guys that were helping us. This fellow here on the left-hand bottom is John Baumgartner. And this fellow here, let's see if I can, that fellow there is Larry Vardaman, and he was the organizer and leader of the RATE project, and he's a very good project leader. He knew just how to crack the whip without making us so mad we quit doing it, and had set goals and raised funds. And I believe it was Larry that contacted me. Someone at ICR contacted me about doing this, and there were 3 creation organizations at the beginning that were sponsoring RATE. One was the predecessor of Answers in Genesis, the Creation Science Foundation, and mostly in Australia then. But then one of them, they dropped out, and for a reason I'll explain in a moment. And then the other 2 were Institute for Creation Research and the Creation Research Society. And they provided a lot of support. So there is Humphreys right there with his hair a different color than it is now. And next to me is the theoretical nuclear physicist, a creationist named Eugene Chafin. And he did a lot of good theoretical work to back up what we were learning. Behind him is Dr. Don DeYoung, who is also a physicist, and he's also a very good science writer. He's easily understandable at the popular level. And so he wrote what Larry called the translation of our technical book into something readable. So, and next is Steve Austin right there in the middle. And he is what he calls himself a soft rock geologist, sedimentary rocks and things like that. And here is Dr. Andrew Snelling. He was the contribution of Creation Science Foundation in Australia. but he changed jobs and moved to Institute for Creation Research about the middle of the project. And then over on the right back row is Steve Boyd, and he is a very good Hebrew, Dr. Steve Boyd, expert in Hebrew, and was a professor at Master's College. And then next to him is Bill Host, who is a student of Steve Austin's geology department. And then after he graduated, went on their staff. And he helped a great deal with, in particular, the project that I'm going to talk about today. And then there's Dr. Ken Cumming, a biologist and dean of the ICR Grad School, and Dr. John Morris, he was then president of the Institute for Creation Research. So those three guys from ICR and ICR in general was a great help to the project. So let's see, what else should I say about that?
Well, how did you personally get involved in RATE, and what was kind of the purpose of RATE? What did you set out to do?
Oh, well, the purpose was we felt that creationists had not really tackled the problem of radioactive dating. There is lots of evidence that a whole lot of nuclear decay has taken place on the Earth in the 6,000 years it has existed, and we felt that evidence wasn't being grappled with. So we were going to tackle the issue head on, rather than just trying to nitpick away at things that weren't very important. So that was the motive. We really wanted to deal with the issue.
Yeah.
So what else should I say, Paul?
Well, that's very, very helpful. So you first convened in, was it 1997? Is that when the first meeting?
The first meeting was out there at the Institute for Creation Research in 1997.
Yeah.
And the project lasted until the year 2005, when we published our second book on radioisotopes and the edge of the Earth, the Red Book.
Yeah, and I've got the two books here. I've got
the Blue Book is the first one.
Right, well, that was 2000, I think, wasn't it?
Yes, in that book we were scoping out what we would do, and I made a prediction about the subject we're going to talk about tonight in the Blue Book, and what we should get when we measure it. So okay. What else?
Well, that's great. So what we'd like to do in this episode in particular is kind of talk to you a bit more about your particular contribution to RATE concerning helium diffusion, the helium research. And as we were thinking about that, we thought, well, maybe a good way to kind of get into that topic is just to recap for our viewers some of the things that we know about radioactive decay, and in particular alpha decay, which is very important when we're talking about the helium work, and what the relationship of that is to helium, what relationship alpha decay has to the helium problem. So perhaps you could just sort of give us set up the background to the problem.
I like to give pictures, so I'll give my some more view graphs, overhead transparencies I used to work with, but they're now slides.
Yeah.
These are zircons, a picture of zircons.
Cool.
And zircons are zirconium silicate. They're not cubic zirconias. Those are zirconium oxide. So they're not the cubic little jewels that get sold in jewelry stores. But these are natural crystals, and these crystals are small. They're microscopic. You can barely see them with the naked eye. And zircons are everywhere there is granite. And so they come from granitic rocks. And here I've got a picture of a piece of granodiorite. And you see the black crystals there. Those are mica crystals, and a particular crystal called biotite.
Mm.
So, and if you look with a microscope at biotite, you'll find these zircons. So I've got a picture of a large zircon, and they come in different colors depending on the impurities in them. But so everywhere there's granite, there's zircons, and then where did we get the zircons we looked at? Well, Robert Gentry, many years ago, uh, got a set of borehole samples that Los Alamos had extracted. So Los Alamos extracted granite, and here I've got a picture of the actual drilling rig that did the borehole 3 miles deep
Wow.
up in the mountains to the west of Los Alamos. And then Oak Ridge, that is Robert Gentry, got some borehole samples and extracted zircons, and he found that there was a whole lot of helium still in those zircons, which, if they were really billions of years old, they should have lost all their helium. And so we wanted to look closer at that and do some experiments. So then Rate extracted these zircons. So there's the microscopic zircons coming from deep within the earth, and the ones we looked at were about 60 germ lengths long. A germ is about 1/millionth of a meter, 1 micron, and these are 60 microns long on the average. Pretty little things. Dr. Gentry furnished that picture. And let's see what else.
So this site where the drilling was taking place, this was a geothermal project, is that right? On the
That's right.
edge of a volcanic caldera.
And that's important. Will be turn out to be important later. That means the rock is hot and dry, and they wanted to extract the heat from that rock. So that's why they drilled this borehole back in 1974, when people were much more interested in geothermal heat than they now are. But we are piggybacking on their research. So now you wanted me to outline what happens with radioactive decay. So these zircons, when they form, grab, as they're forming in the molten rock, they grab passing uranium atoms. They fit in chemically very nicely into the lattice. In place of a zirconium atom, you can have a uranium atom. And so they extract, they grab uranium from the passing molten rock as they're forming. And then at the same time, they reject any passing lead atoms. So lead, I'll mention, is a product of uranium decay, but we know from laboratory experiments that the lead does not enter into the zirconium. It just doesn't fit. It's the wrong size atom, and it has the wrong number of chemical hooks on it. It doesn't fit. So we know from laboratory experiments that zircons contain a lot of uranium and practically no lead. So let's move on. The uranium decays. Now, uranium decays by spitting out an alpha particle. And an alpha particle is 2 protons and 2 neutrons, which is the nucleus of a helium atom. And the helium atom goes out into the zircon or beyond it and grabs 2 electrons and quickly becomes a helium atom. So uranium, when it decays down to lead, it emits when it's uranium-238, the most common variety of uranium, it becomes lead-206, and it emits 8 helium atoms. So I'm just going to run the animation there. You'll see the 8 helium atoms emitted. Some of those go outside the zircons and some stay in it. And from the size of the zircons, we can establish how many escaped and how many were still in the zircon when the decay started. So we know, if we know how many lead-206 atoms there are down here at the bottom, we know how many, we can calculate how many helium atoms were emitted. Now, in this size zircons that we use, the 60 microns, about half of them would stay. And so then what happens to the helium after it's emitted? Would the helium stay in the zircons? Because, another big point, I forgot to mention this. You see the tag there. If you just look at the uranium and the amount of lead, and you use today's slow decay rates then you will get an age of about 1.5 billion years for these zircons. And both Los Alamos and we got the same results, about 1.5 billion years. So that's one type of age and one type of dating technique. So is that clear enough about how Paul is how the
sure.
decay occurs?
So in effect, helium is produced as a kind of byproduct of the uranium to lead nuclear decay.
Right. It goes through
and then I guess the question
of intermediate atoms, and at various stages along the way,
right,
they decay by alpha particles. So you have 8 helium atoms emitted to get down to lead-206.
Yeah. And then I guess the next question is, what happens to that helium once it's produced? What do we know about helium as an atom? How does
I know
it
it's
behave?
in balloons, and balloons float up away
Oh.
into the atmosphere. Is that anything like what happens here?
Well, no.
Okay, great.
But that's a very good question. What would happen to that helium? Would it stay in the zircon? And the answer is no. Helium diffuses out of the zircons, and diffusion is a fancy word for leak or spread out. So helium leaks out of the zircons. So here you see a picture of a crystal, and this big yellow ball in here is a helium atom. And the things we know about the helium is that it's a very lightweight atom. And that means it's fast moving. When it gets hit by another atom, it moves fast. And then the third thing is that it's slippery. That is, it doesn't like to chemically attach to any other elements. So it's called a noble gas. I guess it's noble because it's snooty and it just doesn't associate with other elements. But it's slippery, so it can leak out of the zircons. So now this gives me and us a new way to date zircons. The helium leaks out. Let's just see where the helium atoms go here. Oh, that's a picture of the helium slipping from one piece of the crystal into the next cell, and they go in all directions randomly at different times. So let's see where the helium atom goes now. Helium leaks into that surrounding black mica called biotite. Mica, you may remember, is this flaky stuff. You can peel off thin flakes of it from the rock. And the black mica is biotite, and the helium leaks from the zircons into the biotite. So I'm just going to show some helium leakage here. The little yellow helium atoms are leaking out. Okay. So the question is, how much leaked and how much stayed in the zircons? So let's see if we can determine that. So the answer is that much helium is still in the zircons. So here you see, if you can see my cursor, the depth in the borehole, going from 1/2 mile all the way down to 2.5 miles. And here's the temperature of the rock in the borehole. It's 203 degrees. Los Alamos measured these temperatures when they drilled the borehole. So that depth is 203 degrees, just a little below the boiling point of water at normal pressure. And then all the way at the bottom, it's 530 degrees Fahrenheit, which is about as hot as your oven will get when you're cooking a pizza. Okay, so now I'm at the right-hand column. I'm going to give the percentage of helium that we found still retained of all the helium that was emitted. This is the percentage that was still in the zircons. So I'm going to just start at the top and give you 80, 58, 42, 27, all the way down to 0.1% down at. So you see, as the rock is hotter and hotter, there's less and less of the helium that has been retained, and more of it has been lost.
Makes sense.
And that's characteristic of the process we call diffusion. The hotter the rock, the hotter the crystal, the faster the leakage. So then, knowing these things and thinking we knew that the crystals were, less than 6,000 years old, we could use that data to estimate how fast the leaks were. So we predicted leak rate. So very crudely, this is not the actual math. The math is more complicated, but very crudely, the leak rate is about equal to the amount of helium lost divided by the time we think it's been losing it. So, we estimated this for 2 times. One is the time we thought, according to Scripture, that they had the leak, and that would be 6,000 years. But if the crystals really were the 1.5 billion years that the uranium to lead decay gave, then we should divide by 1.5 billion. So we did that for both 2 models, in other words. And we predicted this well in advance of making some actual measurements about how the leak rates should be experimentally. So here's a graph. These are the predictions. Now, along the bottom, we have temperature, 100 degrees on the bottom, all the way up to 500 degrees. And diffusivity, which is a measure of the leakage rate. And there's a factor of 1 trillion between the top, the fast leak rates, and the bottom, the slow leak rates. So we calculated those in 1998. And then I'm going to show you the first model, 6,000 years, up here where the cursor is. And these little black numbers underneath are the percentages of helium retained, 58 all the way up at hotter temperatures to 0.1%. And these error bars are the errors that, from the crudeness of our information, we could estimate the 95% confidence limits on what we would get with another measurement. So those are the predicted leak rates, and then the other model, 1.5 billion years, we have these leak rates, and they're much smaller because it's a much longer time we're dividing by. So you have to have smaller leak rates to have that much helium still left. So even between the closest points on this graph, it's a factor of 100,000. So we went into print with these predictions. We published the predictions in that blue book you showed, Paul. in the year 2000. Radioisotopes in the Age of the Earth, Volume 1. You with me so far? Am I?
Yeah, no, that's very good. So yeah,
That's
so
a big. I mean,
I think that's very
I'd like to point out here that's a massive difference. This is not a
yeah,
margin of error kind of thing. There's no way one of these is right and one of these is
That
not
is
right.
that is absolutely right. That's a
Right.
very good point to make, Todd. So we started measuring those diffusion rates in 2001 after we published it. We were out on a limb, published in print. Uh, so here are some details about the measurements we made. We extracted zircons from the same borehole and the same depth. And at the left here, you see one piece of the core, uh, and we got it from two depths. Since John Baumgartner had worked at Los Alamos, he had knew some people and knew how to get a hold of the borehole samples. So he went to them and got these two samples. Uh, uh, now, let's see, what's the other thing I should say? Oh, the size. Well, let's go with how we dealt with it. You remember Bill Host from ICR, who helped Steve and I. Bill crushed these samples, and he didn't crush the little zircons within the samples because zircons are very hard. Uh, they're almost as hard as diamond, but not quite. So they retained their shape and their size and didn't get crushed, but all the other minerals around them got made into dust and powder. So then Steve Austin extracted and separated out the different minerals in it, and the zircons are very dense also. So you could separate the other minerals by floating them in sort of dense liquid, and the ones that were left were on the bottom, which were the zircons. So now the extracted zircons had a wide range of sizes, and the size matters. So we sorted the zircons. We sent them to a laboratory in Canada, and we asked for the same size that Dr. Gentry used, 50 to 75 microns. And here's an electron microscope of one zircon. It looks kind of dull. The shininess doesn't show up, and the colors don't show up. But that's a typical zircon.
Wow.
And then what they look like under the optical microscope that the person separating them by size used, they look much prettier, nicely colored, and they're shiny, and I think they're pretty. So that poor worker separated a very large number of these zircons, 1,200 zircons. That's a large number. Usually experimenters in this field, in the geoscience world, will get a few dozen zircons at most, but we didn't know any better, so we collected a large number of this particular size. So next we sent them to an experimenter, and he was an expert. An expert measured these helium diffusion rates. And here's a sample of his paper. The author is Kenneth Farley, and I think he's at Caltech. And this is his apparatus he used to measure the helium diffusion as he stepped up the temperature from this high-powered light bulb shining on the little packet. He stepped up the temperature in steps and measured how much helium went out to the mass spectrometer and at each step. And from that information, you can figure the leakage rates at different temperatures. Now, Dr. Gentry didn't know we were creationists. We went through an intermediate small mining company, and we asked the mining company not to volunteer the fact that we were creationists. So he didn't know Dr. Farley didn't know, and he didn't ask who the sponsors were. But we didn't want him to know we were creationists, which in retrospect turns out to be a good decision. He wouldn't have made the measurements. And he didn't know our goals. He, being a uniformitarian, he didn't read our writings, and so he didn't know about the blue book where the prediction was made, and he didn't know the sites. Now, we told him that after he did his experiment, we would tell him the details about the geologic site so he could write his paper if he wanted on it. But the point is that this was a truly blind experiment. He didn't know what we wanted, and we had no influence over the experiment, and it was done by an expert. So
And
then
presumably as well, this requires some quite specialized equipment, so it kind of made sense to contract this work out rather than try to do it, for example, at ICR.
And the other thing we wanted was if we did it ourselves, we didn't want the uniformitarian world to be able to say, well, those stupid creationists just botched the experiment.
Right.
So,
Yeah.
So now those 1,200 zircons allowed Dr. Farley to go to much lower temperatures. He would start at a high temperature and work his way down in steps. And the amount of helium leaked out at each step becomes less and less. And if there's only a few dozen zircons, he has to stop at a temperature of 300 or 400 degrees centigrade. But we had so many zircons that he could go lower in steps and still get enough helium to make the measurement. And that was an accident. I think that was God's providence that we gave him so many zircons, because it wound up that we are the only ones that have gone as low in temperature, namely to the temperatures in the formation. Those formation temperatures are too low for the experiments normally, but we are the only experiment that I know of that went to these temperatures. So now let's compare his results with the predictions. Here are the predictions again, and then up at the upper right, I'm going to start with some blue dots that represent his predictions, and you'll see whether they fit the 1.5 billion year model or the 6,000 year model. Boom. They fit very well, and they fit the 6,000 year model very well. And you see the little error bars around them. If we repeated the experiments, 95% of the time the dots would stay within the error bars. So, and the error bars overlap very nicely. In fact, the dots overlap very nicely as far down as he could go in temperature. I was amazed, actually, when I first plotted these out on my home computer in Albuquerque. I've never seen an experiment and a prediction match so nicely. And then the other side, the 1.5 billion years, is excluded by that factor of more than 100,000 that you pointed out, Todd.
Yeah.
I've never seen quite so decisive judgment made by experiment between two predictions.
Wow.
So, of course, we were delighted at this. Now, next, we can get a date out of all of this information. So the helium loss divided by the rates that Dr. Farley measured give a helium leak age. Now, here's the percentage helium retained again, and here's the leak rates that he measured, and here are the ages that you get from that. Now, it's not really as simple as dividing helium loss by rate. The math is more complicated, but it boils down to essentially this. Okay, now Dr. Farley wasn't able to go to the temperature where we got the 58% retained, so we couldn't get a leak rate from it for that, but we did for the higher temperature ones. And so here are the results, the ages that you just get. And, they're, a few thousand years difference between them. And that's because of the crudity of our error bars. We didn't have a real precise measurement of several of the things, but those are the ages. And the average, 5,680 years, give or take 1,999 years. I didn't make that up. It just came out that way.
Yeah.
So that's easy to round off. So I'll round both of those figures off. 6,000 plus or minus 2,000 years.
That seems like a familiar number to me.
That's amazing.
Yes. And since it agrees with the face value, no gap date in the Hebrew Bible, the critics really went bonkers over this, especially the skeptics, and it just makes them look hard for loopholes. So
Yeah.
we'll talk about the loopholes in a while. So
that's very, very helpful, and that's explained things, I think, very clearly. I guess one of the questions that people are going to ask is, how do we then reconcile what appear to be two incompatible clocks? Because we've got this helium clock that seems to be giving us an age of about 6,000 years, but you mentioned earlier that the uranium-lead radiometric method seems to be telling us that these zircons are 1.5 billion years old. So we have these two clocks, and they're giving us different numbers. So how do we put that together?
Okay, I'm very glad you asked that. Are you sure you haven't seen this slide before that I'm going to show? Two zircon clocks disagree by a factor of 250,000. So I've just illustrated the clocks by hourglasses. And here's the helium diffusion hourglass giving 6,000 years. So the top part of the hourglass represents the zircon, and the sand in the hourglass, both top and bottom, represents the helium. And it slowly leaks out of the zircon and into the bottom, which represents the biotite. So that's one clock. And then here's our nuclear decay clock, giving the 1.5 billion years. And here it's a little different. The whole hourglass is the zircon, and the red sand is the uranium, and then it slowly drips down through the neck of the hourglass and turns green and represents a lead atom. So uranium to lead gives us 1.5 billion years. Now, you asked how we explain that. I mean, they can't both be right. There must be something wrong with the assumptions or something that went into the measurements. So here's what we concluded in rate. We suggest that the nuclear decay rate changed in the past. So you can imagine a little valve, a thumb valve at the neck of the hourglass, and that got changed sometime in the past from what it is now. So that's why that clock would give a slow long age, because the rates were different. So we think that a lot of these rates changed in the year of the Genesis flood. But there's probably another episode earlier than that where there were high decay rates also.
Yeah.
Does that make sense, Paul?
It does. So for the benefit of our viewers, if I can sort of just try to summarize this. So what you're really saying is that there's a lot of helium in these zircons because there was a lot of nuclear decay. There was 1.5 billion years worth of nuclear decay to generate the helium, but that episode of decay can only have been in the relatively recent past, because there hasn't been time for the helium to leak out of the zircons and escape.
Yeah, the bottom line is that somehow we got over 1 billion years worth of nuclear decay occurring within the past 6,000 years. And the only way I can explain that, or the rate people can, is that there was a speed up of decay sometime in the past. So
yeah, that's very helpful. So so this is great. I was so impressed, when I saw the results of these helium diffusion experiments, when I kind of read the results of this particular rate project. It was very impressive to see the measured diffusion rates kind of falling out on that predicted line. It was so that was quite stunning, really. Now, of course, the critics have your work has not gone unnoticed. Let's put it that way. So the critics have tried to do their best, as you said, to find some kind of explanation, some kind of loophole that will explain the helium work, because they want to say that the 1.5 billion year date is the correct one. So there's got to be something wrong with the helium diffusion. It's maybe the helium diffusion rates were much lower in the past than we measure today, or something like that. So just talk to us a bit about some of the responses that you've had, some of the objections that have been raised from the critics, could you?
Okay. There's an article at creation.com, at Creation Ministries International site, where I summarized a lot of the helium critics and their questions. So here's a picture of the website, and let's see, what do you search for? You search for helium critics up there in the search engine. So you go to creation.com, search for helium critics, and this is the first article that will pop up. The helium evidence for a young world continues to confound critics. So I think this article appeared in 2008, but all of the critics had made their points, including the one that's still hanging on, Dr. Gary Loschelt. They had made their main point by that time. But there's been, the secular world has not been unconscious of this, and a lot of articles measuring the rate of helium decay in zircons have popped up in different kind of studies. A lot of interesting wrinkles to the decay, but in the 2 decades we've had since the results appeared, there's no experimental or observational contradiction. For some reason, they have not made the effort to measure things at low temperatures. They have, by low, I mean, below 300 degrees centigrade, which was where the formation is. It was between 100 and 300 degrees centigrade. So, but they have not done this, and maybe one reason is it's a lot of work to get enough crystals to go to the low temperatures, or maybe there's some other reason. So
Yeah.
Shall I? Where should we go from this?
Well, you mentioned there Gary Loschelt, and I know you've had some sort of backwards and forwards with him in the pages of the Journal of Creation.
Mm-hmm.
And one of the, as I understand it, sort of one of the objections he had is concerns the thermal history of the location, the site where the samples were taken. So if I've got this right, he's arguing that the temperatures at that location were much lower in the past, and therefore the helium diffusion rates would have been much lower. Perhaps you could just sort of talk a bit about that and about the thermal history of the Fenton Hill location.
All right. Show a slide here that kind of summarizes his objections. This is the low shelf loophole. He's the last of the critics. The others seem to have gone away for some reason. First, he ignores rates data at low temperatures. And then secondly, he ignores the existence of a ice age volcano blew up according to the secular measurements of dating. The volcano blew up about 1 million years ago, and that borehole you saw is perched right on the rim of that old that volcano that blew up in the ice age. So here we see a plot of temperature on the bottom. This is 0 degrees C, centigrade now, up to 500 degrees C. And the black dots are the measurements, and the squares were the predictions we made from the amount of helium that was lost in 6,000 years. And the black dots and the squares line up nice. But Gary, if I may call him by his first name, I've had 2 years worth of talking with him, both face to face and by email. And I was trying to understand his theory. So I'm going to try to give the best view of it I can. Gary thinks that all these low temperature points, the black dots and the squares, are just a fluke, and the real diffusion rates in the formation continue down this straight line on down to very low temperatures. And then if you just take the loss rates and slide them over from present day temperatures on down to the temperatures he wants, he has a lot of those points being between 150 and maybe a little less than 100 degrees C. And if you slid the points over to the high temperatures that are there today, but drop these predictions down to the level you need to keep the helium in them, there's over 100 million, factor of 100 million between those two. So he wants to slide these points over, and he wants to ignore the low temperature points we measured. Now, so if either one of these things is absent, his theory won't work. So he's got to have both lower temperatures in the formation, and he has to have his theory that causes us to ignore, or causes him to ignore those low temperature measurements. You know, just one of those two factors will not work. They're not enough. So now let me see if I can explain why he thinks we should ignore the low temperature measurements that we made. He thinks, and I think he's actually right, but some of his assumptions in it are not. But he thinks that there are two domains within the crystal. One is a domain that really retains the helium very well, and so the leak rates out of that domain, you could imagine, as just two different parts of the crystal, but they actually overlap. He's imagining that high temperature domain. What am I going to say about that? Leaks helium very slowly. So he calls that the high retention domain. And then in the in the actual formation, there's a low temperature, a low retention domain. And so he has that domain not being emptied out in the long time that he thinks it was there, because it was hindered by the biotite surrounding it. And so, so when we took the crystals out, the low retention domain still had some helium in it. And then in the lab, where there's no biotite, just a vacuum, that low retention domain would leak and provide these measurements that we got at low temperatures. But he's saying that in the formation, this leakage wouldn't happen. So that's essentially. So he's tried to publish that theory and hasn't been successful. But a couple of the long age sites, such as Hugh Ross and Gary, who's the other? Randy Isaacs, the American Scientific Affiliation. They published his theory without peer review, but it's on there. And that article I showed will give some of his references for that. So, how do I answer that? First of all, I don't think he's actually kind of invented his own temperature history, and it really ignores what Los Alamos calculated the heating of that formation would be from the volcano. I don't know exactly how it gets around that, but the nearby volcano should have heated that formation and supplied most of the heat that we now measure. And if it was that hot, then it would, he needs low temperatures persisting up until about 10 or 20,000 years ago. But the volcano was supposed to be 1 million years ago, and it should have heated the formation up. Now we think that that formation has been about at the same temperature for thousands of years, and it's in hot, dry granite-like stuff, and the heat flow rates in dry rock like that are very slow. So if you just extrapolate backwards in time from today's temperature and assume that it was cooler, you don't get very, very low by 5,000 years ago. So, in other words, I don't think his theory works.
So. Yeah. So it looks as if the rate helium work has been quite resilient, in the face of the critical objections. So I guess we probably haven't sort of heard the last of this. There's probably this discussion is going to go on. One thing I did want to just briefly talk about before we close out, and we're getting very close now, I think, to the end of the episode. Are there plans to do further research, creationist research in this area? If
Yes.
so, what might that involve?
They're out of the planning stage, and there's an effort going on. Now, I'm not directly involved in it, but there's an effort going on to take some other sites and take the large amounts of helium in those sites and make similar measurements. So we need to find somebody, because Dr. Farley doesn't want to do it. We need to find some lab that can do the measurements for us.
Yeah.
So I have a couple of other loopholes that earlier critics on my slides, if you want to see those.
Sure. Why not? Yeah.
Okay. Let's see. This is the Ross loophole. Hugh Ross said on a radio program that there was a whole lot of helium on the outside of the zircons in the biotite, huge amount actually, and it leaked into the zircons. But the data say no. Diffusion occurs from high concentrations going to low concentrations. And the amount in the biotite, there's helium in the zircon and there's helium in the biotite. And the concentrations in the zircon are about at one particular depth were about 800,000 trillion atoms per cubic centimeter. And in the biotite, from that same depth, there are only 4,000 trillion per cc. So the leakage would go from the zircon to the biotite like this. So the helium is diffusing out of the zircons, not into it. So that was the Ross loophole. Let's see. And by the way, yes, something kind of interesting. If the biotite flakes are much larger, and if you take that low concentration in the biotite and multiply it by the larger volume, you get about the same amount that has been lost from the zircons. You find that in the zircons. In the biotite. So the total helium in the biotite is about equal to the helium we know was lost from the zircon. So we know where the helium went. A fellow named Henke said that down in the borehole, the pressures were higher, and that stopped the helium from leaking out of the zircons. It turns out that it doesn't matter according to measurements, and the reason is that the zircons are very hard, and the pressure can't compress them. These pressures in the borehole. So now the biotite is compressible, and we accounted for the compression, the pressure in the biotite. So there's more at that creation.com article that I cited. So let's see. Really sophisticated one, I thought, was by Hugh Ross's expert on radioisotope dating, Roger Weems, who is a geoscientist at Los Alamos and studies that. And he suggested, maybe the zircons started off with no radiation damage, and the uranium in them made radiation damage, and that made leaks. Turns out it doesn't really matter. Suppose that the zircons were very pure at first, and that only radiation defects amount to anything. So I'm going to, I think, run a simulation showing the radiation popping up in the zircon, making little holes, little tunnels in it. If that happens, it only changes the results by a factor of 2. Sort of like, whatever the age of the zircons is, the average age of all those defects is half of that. So that's far short of the 100,000 factor of 100,000 that Roger needs to explain that. So the last loophole I'm going to talk about is an early Ross loophole. In an earlier radio program, he said something like, "Helium is slippery, so you can't rely upon it." But we want it to be slippery. That's what we want, and we want helium to slip down from the top to the bottom in the hourglass. So other than that, helium's just fine for measuring the age of the zircons. So that's all I had to say, but maybe you've got some more things to add, Paul. Do you want to ask about some more stuff?
Well, no, I think that's covered the main sort of loopholes, certainly that I've sort of come across. I understand you also published an article about argon diffusion. based on some data from the mid-'80s, which sort of confirmed the helium results as well.
I'm glad you asked about that. I'd forgotten to even mention that. The same borehole, rocks from the same borehole, and granite from the same borehole has a common mineral called feldspar. It's a sort of shiny, milky white mineral, and that has potassium in it, and the radioactive potassium in it decays to argon. And some researchers using those data from that borehole calculated that the temperature must have been very low before about 5,000 or 6,000 years ago, because there was essentially no loss of argon. So the amount of argon that was lost is consistent with just 5,000 years or so of argon loss out of the feldspar in that borehole. So they're essentially, making the temperature very low before 5,000 years ago, just arbitrarily, and so that's pretty much the same thing as saying the feldspar didn't exist before about 5,000 years ago. So yeah.
That's great. Yeah, thank you so much for explaining all of that. For our viewers and listeners, we will definitely put links in our show notes to all of the relevant papers that have been referred to during this episode, so you can check those out. And I'd also say to anyone who is listening to this in audio, if you're listening to this on a podcast streaming platform rather than on YouTube, come to the YouTube channel and watch it in video, and you'll see all of the fantastic slides as well. So don't miss out on doing that. Come and subscribe on YouTube as well. Russ, it's been absolutely great to have you. We're so glad that you could come and join us today, and that's been fantastic. And Todd, I don't know what we've got coming up next time. As we often say at the end of these episodes, it's a magical mystery tour. We're not quite sure what's happening next, but I'm sure it's going to be a lot of fun anyway. So we will see all you guys in a couple of weeks' time. We'll see you then.
Thanks for listening to this episode of Let's Talk Creation. For more information, visit us at letstalkcreation.org, where you'll find an archive of past episodes and all our show notes. If you'd like to leave a comment or make a suggestion, you can find us on all the major social media platforms. Let's Talk Creation is brought to you in the U.S. by Core Academy of Science and in the U.K. by Biblical Creation Trust. As a listener-supported ministry, we are grateful for all of your financial support. Find out how you can make a contribution at our website, letstalkcreation.org. Also remember to like, subscribe, and share this episode with your friends. Thanks, and see you next time.